I will now talk more about printing, not mastering. My colleague did this morning. So we can direct print couplers on optical chips. And I think most of you already know Nanoscribe. I think so. I can skip that slide. But maybe what is a little bit interesting is we have a very broad range of applications, as you can see here on the slides, from life science, micro-optics, which Jim presented, microneedles. A lot of things is still in academia, but where we think it's and where it's going to industry is photonic packaging or integrated photonics, and that's what I'm going to talk about today. Again, key technology is on our website. You can have a look at there, or you can come by the booth. We have white papers on it. Just one thing, a little bit about our grayscale technology. How does it work? So, which is key to the printing process we do. We tune the laser intensity, which then tunes the voxel where we print. Okay, so we can have a larger layer than normally in 3D printing, and can tune nicely the voxel while scanning the line. Is this understandable? Was it too fast? Yeah, okay, let's go ahead. With this, we print on any kind of surface, any kind of shape. So we print on fiber arrays, on the chip edge. We can print on chip surfaces, which then maybe can be nano-imprinted later on with EVG tools. So there's a broad possibility to enable low-loss optical coupling in the integrated photonics area. How do we do this? Here is an example for fibers. So we have workflow-based software which enables an easy setup of the process for prototyping or for mass production. You can define the lens sphere formula very easily. We have a precise alignment to the fiber core, so we detect the core within 500 nanometer precision. 8 fibers, 32 fibers, we don't really care. So we look really where the light is going and have the lens, which you can see here in the middle, for example, the collimation lens. That's some periscopic lens for wafer level testing, and they can precisely be aligned into the direction of the light emitting. You can see also what we have in-house is we have the possibility to do some in-house simulation. So it's an in-house tool and an in-house tool to do the measurement. So you will see also on the other slides there is always a simulation and a measurement, and we can really nicely iterate the printing process to have a precise shape. Here on the table, you can read it by yourself. We have some typical values what are expected and required. So metrology was a question. We use a confocal and an SEM to validate the shape of lenses and optical elements. We have done the typical thermal and temperature cycles and humidity tests, and it even works with cryo temperature. So we have customers in quantum technology using all of this kind of lenses in cryo. Some examples right now. So this is an internal demonstrator for measuring losses. So we have single mode. Everything is optimized for single mode fibers. So this is just to show with the light how it's passing through these kind of periscopes. With a 3 micron mode filter in the middle, so they overlap. This is basically the ideal case to collimate the light, and so we have down to 0.3 loss per coupling interface. This shows the variation of shapes we can do from collimating lens, tapers, periscope. You imagine it, you name it. We can print it on fiber arrays or on single fibers, endoscopes. Broad range is possible. Larger look at the periscope lens. You need to be aware that we have an adaptive printing process, so the bulk material, in difference to imaging optics, is printed very fast. We don't care about the optical quality, basically. It's not imaging. We steer the light and we form the light, and then only this part on the upper area is printed with optical quality. This is an image of fiber-fiber coupling. Next, what we do is, as I mentioned, is printing on chips. So we can detect on the side of the chips markers, which we defined previously in the software. We can detect the edge of the chip, which is important to know where you want to print. And also we have a precise internal technology that we make sure if you print on the edge of a ship and you have the light coming like this, so you have some shutting. You lose power and you can disturb the process. So we have internal easy process. It's standard recipe for you when you use the system that we don't lose power, that we can print even to 200, 300 micron below the ship edge, which is quite important for some applications. So the result is then here, this is from handheld OCTs, this is for OCT system, where we printed these kind of lenses on the edge. And this here is from Epix Fab, it's a SOA taper, SOA material. And here again, simulation and measurement are overlapping very nicely. I didn't mention print times here. For example, it's 90 to 180 seconds. Depends on the volume, on what you have as a mode field on the chip. So we typically start with ideally with a mode field of 2 by 3 micron, and also most of the time it's elliptical if you print on a chip. So you want to transfer this to a fiber or in free space, so we can have an aspheric shape or freeform shape, transferring the elliptical beam to a round beam very easily. This is some examples. I did a second slide because you cannot really see a lot of things here. So you have the fiber array here. So here's a little bit more an explanation. So we have a collimated light coming out of this fiber, and then we have a collimated lens on this area, and we couple from one side to the other. So basically, this is an ideal case for coupling. The collimation diameter of 25 micron gives you 24% of it, so it gives you something like plus minus 6 micron of 1 dB lateral alignment tolerance, which is quite nice. So you can do pick and place. That means you can go to several hundreds or thousand pieces per hour. We had, in this case, less than 1.3 dB coupling loss from the fiber to the SOI chip. We are still some optimization the lenses on the chip, so it's not the end of the line. We can have already shown less than 1 dB. This is just also, it gives you an idea what you always have on these kind of chips. You have the waveguides, you have loopbacks, so the classical things you need on kind of big chips. And large image of the handheld OCT chip again. With silicon nitride, this was for 1060 nanometer to show also that we print on other platforms. Also what comes more and more is vertical coupling. So this is one example where we have done this. This is for single nanovia avalanche photodetector from Pixel Photonics, a startup in Münster. They use our technology to print this kind of tapered broadband coupler. And you can see here the reproducibility of the losses of these couplers in this diagram. And this is working under cryo operation, basically. So several cycles up and down, and the losses are quite reproducible and stable. I mentioned here print time is below 60 seconds. I visited them 2 weeks ago. They're at 30 seconds right now for a single coupler. And they are 16, 18 on a single device. Again, larger image. And this is a tapered mirror. So the crucial thing here you see the alignment markers. So to detect the markers, we can do below 100 nanometer, 200 nanometer detection precision. And the crucial thing is really print precisely to the taper in order to minimize the losses so that the mode, the light is going into the guide or coming out of the guide depending on which direction the optical system is set up. What I also want to show is other things we can do. So we can not only print 3D optics or 2D optics. What we get more and more is some optomechanical elements like these clamps for fibers. It's not for mass production, frankly speaking. You can maybe optimize it for small series. This is really for prototyping and small series, where this is highly interesting, especially when you, for example, can combine it here with a lens and then coupling into a grating coupler. So you have a really high reproducible positioning of these kind of fibers. We did this manually for this kind of setup in-house in Karlsruhe. But you can imagine it can be done with a pick-and-place system very easily. For this, to finish, we have the Quantum Mixer line, dedicated system we developed. So that is our application lab. It's one of our process engineers on the system. And summary on the optical specs. So we can go down to 5 nanometer roughness, shape accuracy 200 nanometer. That's most of the time more than enough for the applications. There's a 6-minute by 8 lens fiber array. It's even less now. So we have 25 seconds for focusing lenses, for example. We can handle up to 8-inch wafers, which is important. So you can do wafer level processing. And we have the automated alignment procedures for chips and for fibers, which use 2 different technologies. I can explain the technologies more if you want, if you can come by the booth. So as said, we supply software, hardware, and the printing material. I think that's still important. So here you can see just a spotlight on what type of materials we have. You see the refractive indexes up to 1.6 we have, which is interesting for vertical coupling to reduce losses when you print a prism or a parabolic tear mirror, for example. This gives, again, an overview. If we can go from prototyping, mastering, and direct writing scale manufacturing very easily with our technology. So we have broad range of possibilities. Prototyping, I would like to mention a little bit also with regards to EVG. What happens is often that we also do not only prototyping. This is clearly, that was an hour print. That's not for mass production. But we did the prototype, and the customer has gained per iteration 6 months, roughly. Okay, there's no other way to do this kind of 300 lenses on the grating couplers. There's no other possibility to do that. Thank you for your attention.